Welcome to this lecture in our particle characterization course. In the previous lecture, we had discussed particle structure characterization, and then we started discussing aspects of surface interaction with its surroundings. Now, before we continue that discussion, I just want to take a minute to list some textbooks that you will find useful in order to learn more about the topics that we have been discussing. The first part of the course, particularly the shape characterization and some of the earlier methods of size characterization, are taken from the book by Beddoe, Particle Characterization in Technology. So, as far as a single textbook is concerned, that would be the most useful for you to refer to. The book by Venkateswarlu and Prabhakar Rao on particle technology also contains much useful information. The book by Allen on particle size measurement covers some of the more recent aspects of size measurement technologies, in particular based on dynamic light scattering techniques and submicron particle size measurement as well. Finally, the McCabe and Smith book on unit operations of chemical engineering, I am sure many of you have referred to it in the past, does contain many references to particle technology, particulate processes and particulate characterization. So, these are a good set of books to refer to. Now, in addition to this, there is much reading material that can be accessed through recent journal publications. Particle characterization is a field that is evolving virtually daily, and so it's important that if you are really interested in staying on top of this technology, you have to refer to current publications, both conference papers as well as journal publications, in order to be fully up to date on what is going on in this field. So, easiest way to do that is, if you have access to a search engine that can look into literature, just type particle characteristics or particle characterization and you will come up with a lot of references. In one of the later lectures, I will also give you a list of more recent publications which deal specifically with aspects of particle characterization that we are now starting to cover and which we will be covering in future, aspects such as particle adhesion, cohesion, particle removal from surfaces, particle transport, particle deposition, as well as functional properties of particles. So, we will be referring to a different set of books which cover those aspects in more detail. Okay. So, coming back to the topic under discussion, the way that a particle interacts with its surface is primarily characterized by the outer surface, although as we saw, certainly in aspects such as adsorption and absorption, the subsurface can also play a key role by either by enhancing or by delaying the rate at which transport is happening between the surrounding fluid and the suspended particle. In particular, adhesion of particles to surfaces as well as to each other is of grave importance in many manufacturing industries. In many, particle adhesion is to be avoided. For example, coming back to semiconductor manufacturing, if you are making a silicon wafer or a circuit, it is very important that the electrical paths that have been laid out on the wafer remain intact. A wafer or any semiconductor is designed such that there are specific conductive paths, there are specific semiconducting paths, and there are specific insulating paths, and you want to keep them separate in order for the device to function. Now, imagine that you have a conducting area. Let us say that you are supposed to have electrical conduction occur between these 2 points. Supposing an insulating particle drops into the middle of this conductive section. This could be, for example, a plastic particle, or even something as simple as clothing fiber or human skin or hair, which is essentially non-conducting compared to the metal conductor that the device is based on, what that's going to do is essentially short this circuit. Or alternatively, if you have two parallel paths which are designed to be non-conducting and you get a conducting particle deposit so that it bridges those paths, then you get a conductive path which is going to interfere again with the functionality of the device. Now, if this phenomenon is instantaneous, in other words, a particle comes, sticks to the surface and then is removed, then there is no long term consequence of the particle. It may cause a yield loss in your manufacturing line, but may not cause a reliability hit in the field. However, if this particle has a high adhesion force, then it's going to stay there virtually forever. So the device is never going to function in the field. So it's not a short term problem, it becomes a long term problem. So in this particular illustration, the adhesion forces of the particle that bind it to the surface play a huge role in determining whether it is a simple early life problem or whether it is a long term reliability problem. Now, when we talk about particle to particle cohesion, this again for the most part is something that you want to avoid in manufacturing processes. The whole reason for preparing a particulate slurry or a suspension is to keep the particles separate and isolated as particles. So it kind of defeats the purpose if two adjacent particles simply come together and stick to each other. So in this case, the particle to particle adhesion in a medium, which is also known as cohesion, is something to be avoided. Now there are many reasons for this. For example, again in the pharma industry, the processability of the powder is an important issue. If you are taking, for example, a pharma powder and you have to transport it from the vessel in which you are manufacturing it into a container into which you want to fill it or into a capsule form, you have to transport it across tubes or some kind of plumbing that you send this suspension through. When particles are discrete, the suspension acts like a Newtonian fluid. When the particles start coagulating, it starts to behave like a non-Newtonian fluid. So there's a tremendous difference in the flowability characteristics of any suspension depending on whether the particles stay isolated or whether they start conglomerating. So clearly adhesion of particles to surfaces and to each other is of huge practical significance and it's worth studying it in more detail. People have actually done empirical experiments on particle adhesion to surfaces. In fact, there is a class of experiments that have been done on metal surfaces that are very clean, where the metal surfaces don't have any oils or other types of contaminants on them. And particle adhesion force has been studied as a function of particle size close to room temperature. And when all the data were gathered, and this really consists of virtually millions of data points, and the data were analyzed and the data were fitted with a model, the model that came out looked something like this: F adhesion expressed in dynes equals 150 times dp, where the particle diameter is expressed in centimeters, times 0.5 plus 0.0045 times percent relative humidity. Now this is an interesting equation because it says that adhesion forces basically scale as particle size. In other words, the larger the size of the particle, the greater will be its force of adhesion to a surface, and it's basically a linear dependence. It also says that the relative humidity plays a huge role in this. In fact, when you go to 100% relative humidity, this term becomes comparable to this term. You are essentially doubling the adhesion force, and the reason of course for that is relative humidity is basically moisture, and when moisture gets between the particle and the surface, you form liquid bridging as well as solid bridging, which can provide very high adhesion forces. It's basically a surface tension phenomenon. But even in the dry case, you can see that there is a fairly clear linear dependence of the force of adhesion on particle size. Now, that is interesting because when you actually look at the forces that bind particles to surfaces or to each other, there is a fairly large number of them. So, given that this fairly simple and straightforward dependence that has been observed experimentally is useful and to some extent surprising, because it is somewhat counterintuitive. What this equation says is larger particles have higher adhesion force to the surface, but if that is true, based on your practical experience, you would have seen that if you have a number of particles on the surface and let us say you blow on them, which particles will be removed first? The bigger particles, right? Now, how is that consistent with what you are saying here? If it is true that larger particles have greater adhesion force, why is it that when we employ a simple cleaning procedure like blowing on it, you always remove the larger particles before the finer particles? Think about it. It's something we'll get back to during the course of the next few lectures. Now, I said that there's a variety of adhesion forces that bind a particle to a surface. What are some of them? We already talked about van der Waals forces yesterday. These are the forces of intermolecular adhesion which would prevail even when the particle is completely dry and the surface is completely dry, or the two particles are completely dry. The second are electrostatic forces. Again, electrostatic forces would apply even in a completely dry environment. And by the way, when we talk about electrostatic forces, they can be subclassified into three types. You have your Coulombic forces, which you probably studied about in electrical engineering. Then you have what are known as image forces. The difference between these two is Coulombic forces apply when both the particle and the surface are charged. The image forces apply when only the particle is charged and the surface is not, and we will look at the difference between these two. Then you have what are known as contact potential forces. So, the net magnitude of the electrostatic forces is a combination of all of these. So, what are some of the other forces that prevail? There are also ionic double layer forces, which prevail when the intervening fluid between the two particles or the particle and the surface is a liquid, and because of the presence of ions in solution which preferentially solvate the particle and the surface, you build up a charge, and that leads to forces of either adhesion or repulsion, and these are represented by zeta potential. Another type of force is what are known as steric forces, which is a name for surface tension based forces. So, the wetting or non-wetting of a surface plays into this. When we talk about steric forces, again they can be subclassified as wetting and solid bridging forces. When a liquid first wets the interface between a particle and the surface and provides an additional adhesion force, that is called a wetting action. Now, if you take that same interface and you dry it, then the adhesion force actually increases by several orders of magnitude, because the liquid that is trapped between the particle and the surface now solidifies and actually forms a solid bond between the two. So, that is called solid bridging. Then you have hydrophobic hydrophilic interactions which essentially dictate whether two surfaces are going to attract each other or repel each other, and it takes into account the properties of the intervening medium. So, the way that two hydrophobic surfaces will react will be very different depending on whether the intervening fluid is also hydrophobic in nature or hydrophilic in nature. Similarly, the way that two hydrophilic surfaces will interact will depend on whether the intervening fluid is hydrophilic or hydrophobic. So, we will discuss that also in a little more detail later on. Now, in addition to this, there are a variety of forces that apply in specific situations. These are forces that are universal. Whatever the combination of particle and surface, you would expect these forces to apply. But there are other forces such as magnetic forces. Obviously, if you have two magnetizable surfaces, the adhesion force between them or the repulsion force between them will be dominated by the magnetic field that is set up between them. Another example is sintering. This is especially important in metallurgical casting processes where you can provide an extremely high binding energy between one material and the next by sintering them together, by applying essentially a high temperature process to glue them to each other virtually. So, sintering provides extremely high bonding forces. Another classification would be physical entrapment. Which can happen when, for example, the surface has certain features that the particle can latch onto or lock onto. So, for example, if the surface has cavities and the particles essentially settle into these cavities, that would be an example of a surface feature that provides entrapment of the particle. Another example would be porosities that particles can diffuse into and get captured. Another example would be matched roughness elements. If two surfaces are brought together in such a way that their roughness asperities are used to interlock them together, that would be another physical entrapment. So, these again, these are examples of forces that are somewhat unique to the application, but which provide adhesion forces that are far in excess of the forces that would apply otherwise in the absence of these fields. Now, compared to all this, the final force that we are going to talk about, chemical bonding, can be orders of magnitude higher. It's just like physisorption versus chemisorption. While physisorption can be an intense phenomenon, chemisorption in theory can be orders of magnitude larger, because here you are not only using physical bonding, you are also using chemical bonding. So, this is a situation where the surface that's being approached by a particle is actually capable of chemically reacting with the particle, or two particles that are approaching each other can have not only physical interactions, but also chemical interactions. Now, in that situation, the interactive force between the two particles or the particle and the surface can be very large, and also it can be irreversible. One of the things we should also mention is that all these other forces we have been talking about are in principle reversible. If a particle is trapped on a surface or attached to a surface, you can always do something to remove it. However, when the process of bonding is chemical in nature, it may never be possible. The process may be entirely irreversible. So, depending on whether we want the adhesion to happen or not, you might either want to promote such chemical bonding or preclude it from happening. Okay. All right. So, you have so many possible forces that can apply when you have two surfaces in contact, and we haven't even covered, I mean, when you talk about field induced adhesion, there are so many varieties of forces that can be applied. For example, you can even use a thermal gradient. Just like a thermal gradient can induce a velocity, a thermal gradient can also induce adhesion of a particle to a surface. You can build up charge by various mechanisms. Triboelectricity can be used to bond particles to a surface. But even without considering all this, we have a large number of potential adhesive phenomena that can bond two surfaces together. So we'll deal with some of these in more detail, starting with van der Waals forces. Again, van der Waals forces are very fundamental because that's where it all begins. All you have to do is bring any two atoms together or molecules together or particles together, and there will be an immediate atomic level force that is set up between them, and that's called the van der Waals force. Now, so what van der Waals force is, it's basically the sum of all the interactions that are set up due to induced dipoles between adjacent atoms. So these are essentially dispersive forces in nature, and they start as soon as you bring two molecules together. All it requires is the presence of the molecules or the particles near each other for this force to be set up, and it's a summation. So if you have many atoms, many molecules, and many particles that are in contact with many neighbors, the net van der Waals force is much higher. Van der Waals force, as we again discussed in the last class, is characterized by a parameter called the Hamaker constant. The Hamaker constant is the most fundamental representation of van der Waals forces binding two surfaces. The Hamaker constant, therefore, plays a huge role in determining the force of adhesion between two surfaces, particularly under dry conditions where some of these other forces that we have been talking about do not apply. So this F van der Waals is a function of Hamaker constant of the system. The Hamaker constant is represented here by A, and this A itself of the system is a function of the Hamaker constant of the interacting bodies Hamaker constant of the intervening fluid and the other properties of the intervening fluid. So for a system where you have, let's say, a particle and a surface with some intervening fluid, let's call this 1, 2, 3, then A system equals A132, the Hamaker constant for the entire system reflects the Hamaker constants for 1, for 2, and for 3, as well as the various physical properties of the intervening fluid. The van der Waals force itself, F VdW, is a function of A132, but it's not only a function of the Hamaker constant. The Hamaker constant is one of the key parameters, and it's mostly a linear dependence. As the Hamaker constant increases, van der Waals force will also increase, but there are other parameters that also dictate the van der Waals forces. For example, the geometries of the bodies. For example, two spheres will interact very differently compared to a sphere to a surface, compared to a cylinder to a sphere, and so on. So the geometry of the bodies plays a significant role in determining adhesion forces. It also depends on the distance of separation, as with virtually all forces of attraction or repulsion, the distance of separation between the bodies will play a significant role, and for the most part it will be an inverse dependence, right. It will go as distance linear or distance squared or distance cubed, but in any case force will typically fall off with distance. And again, the properties of the intervening fluid will also play a role in determining the van der Waals forces. The Amaker constant, by the way, is itself a function of the molecular properties of the fluid. Now, how do you calculate the Amaker constant? There are really two theories of calculating Amaker constant of a fluid. So it depends on molecular properties. And the two theories are London theory and Lifshitz theory. The London theory is also known as the microscopic theory, and the Lifshitz theory is known as the macroscopic theory. So according to the London theory, you can calculate the Amaker constant by characterizing piecewise binary interactions between adjacent particles and then adding them up. So that's why it's called a microscopic approach, because it looks at individual pairs of atoms or molecules or particles, estimates the forces of interaction between them, and then kind of does this sequentially and adds them all up. The Lifshitz theory, on the other hand, is based on quantum electrodynamics. It looks at the entire system and applies wave theory to calculate the interaction forces between particles. It allows action at a distance. The difference is, in the London theory, you are assuming that only the adjacent particle can exert a force on the particle nearest to it. In the Lifshitz theory, a particle that is further removed from a particle can exert an influence on it, essentially by propagation of waves of energy. And that is a primary difference between the two. But these two theories are used quite extensively to calculate Amaker constants for systems. So let's look at some examples of how the geometries of the bodies as well as the properties of the intervening fluid play a role in determining the van der Waals forces of adhesion. The first case we will look at is a surface and a spherical particle that's close to it. So let's say that the diameter of the particle is some dp, and this distance from the end of the particle to the surface is some z0. And again, let's call this material 1, the surface is material 2, and the intervening fluid, let's call that material 3. For this particular geometry of a spherical particle that is in near contact with the surface, the corresponding van der Waals force is given by, again, A132 certainly appears again in this equation as well, times dp divided by 12 z0 squared. So in this case, in the case of a sphere interacting with the planar surface, the van der Waals force is proportional to the Amaker constant, it's proportional to the diameter of the particle, and inversely proportional to the distance of separation between the particle and the surface. Let's look at a case where, again, you have a planar surface, but now you have a cylindrical particle of some length L and diameter dc, and let's say that this again is the distance of separation between them. In this case, the van der Waals force is given by again A132, but now there is a square root dependence on the diameter of the cylinder divided by 16 times Z0 to the power 5 by 2. So, just by changing the shape of the particle from sphere to cylinder, you change not only the magnitude of the adhesion force, you actually change the qualitative nature. For example, even the dependence on diameter is different, as is the distance dependence, the distance between the object and the surface. The third case we will look at is two surfaces that are in contact. Here again the distance of separation is some Z0, and there is an intervening fluid just like in the other two cases. So, here what is van der Waals force? It is again A132. Of course, there is no characteristic diameter now, it is just two planar surfaces. In the denominator you have 6 pi Z0 cubed, where Z0 is again the separation distance between the two surfaces. So, if you compare these three equations, the only thing that is common to all of them is the linear relationship between adhesion force and the Hammaker constant. All the other dependencies change based on the geometries of the objects. So, that is something that is very interesting and something that you can actually use to your benefit when you are in a manufacturing environment. Now, how do we define this A132 parameter? A132 is the Hammaker constant for the entire system, but obviously it will depend on, as we said, the Hammaker constants of the individual objects as well as the intervening fluid. So, A132 is defined as A12 plus A33 minus A13 minus A23. Now, what do we mean by that? A12 equals A11 times A22 to the power half, and similarly A13 equals A11 A33 to the power half, and A23 equals A22 times A33. What is A11? It is a Hammaker constant representing the interaction between two particles of the same material 1 without an intervening fluid. So, essentially when you bring these two particles together in vacuum, this is the Hammaker constant that characterizes the interaction. Similarly, A22 is for bringing two particles of material 2 together. A33 represents the Hammaker constant for bringing two molecules of the fluid together, and A13 is then the Hammaker constant associated with bringing molecule of 1 and molecule of 3 together, which is taken as the weighted the square root of the individual Hammaker constants. So, you can calculate the associated Hammaker constants using these rules, and then you can proceed to estimate the van der Waals forces of adhesion. Now, where does the nature of the fluid come into play? Obviously, the A33 parameter is critical, and it turns out that A132, the Hammaker constant for the system, if you have air as your intervening fluid versus if you have again A132 with water, if you take the ratio of the system Hammaker constants, the only change being 1 and 2 are the same, 3 has now been changed from air to water. What do you think will be this ratio? Will it be close to 1, less than 1, greater than 1? Much greater than 1. In other words, the Hammaker constant is much lower when the intervening fluid is a liquid such as water. Now does that have practical implications? I think you all know from your everyday experience that it's easier to wash dishes, for example, when you have soaked them in water, right? Why is that? One reason is that as soon as you take this dry interface between whatever it is, food particles or dust particles and a plate or some other solid surface, the Hammaker constants are very high. So the food material is strongly adhered to the surface. As soon as you soak it in water, the Hammaker constant drops by an order of magnitude, by about 10 times. So the effective A132 also drops, not by 10 times, maybe by about 5 times, and because of that the van der Waals forces of adhesion also decrease significantly, and that is why wet washing is always easier to accomplish than dry cleaning. That is one important implication here. The other thing that we should think about is when we talk about Hammaker constants, it is not only a geometry dependence, it is also a material dependence. Different materials, for example, why would A11 be different from A22? For example, if material 1, the particle, let us say is a metal, and 2 is a semiconductor, what is going to be the difference in the Hammaker constants for the two? The material dependence of the Hammaker constant is again something that we really need to fully appreciate in order to make use of it in a beneficial manner. So if you take metals, then you take semiconductors, take plastics, and you take elastomers or rubber materials. What do you think will be the approximate range of A values? Which will have the highest and which will have the lowest? The magnitude of the Hammaker constant goes this way. Metals have the highest Hammaker constants, semiconductors have less of a Hammaker constant, plastics even less, and rubbers even less. In a way it is related to the hardness of the material. That is one way to visualize it, and as we discussed earlier when we were talking about surface energy, there is also a relationship of surface energy to Hammaker constant. Metals and semiconductors are high surface energy materials. Plastics and elastomers are low surface energy materials, and that is why there is also this dependence on the material type. When we take a metal and when we say it has a high Hammaker constant, what it means is anything that it comes in contact with will accumulate on the surface and stay on the surface. Now that may be again beneficial if you are using the metal surface as a collector for something, but sometimes it is harmful. For example, if again the metal is something you are making your hard drive disks with, you do not really want material to stick to it. So what you can do is apply coatings to it, right? I mean if you want to take a high surface energy or high Hammaker constant material and change it into a low surface energy or low Hammaker constant material, just coat it with a low surface energy material. So for example, polymer coatings on metals are typically employed to reduce their surface energy, to reduce their Hammaker constant, to reduce their van der Waals forces. How do you increase the, or how do you reduce the surface energy or Hammaker constant of a plastic? Well, the harder the plastic, the more energy that it has, or the higher the Hammaker constant that it has. So if you mold the plastic so that it is softer, essentially you can actually make it less binding to the particle. So the use of, for example, composite structures is one way where you can accomplish it, although in many cases the composite material will actually increase the rigidity of the structure. So, you have to design the system in such a way that whatever material you add as a composite actually reduces the hardness or surface energy of the material. For example, carbon fillers are typically, while they are strong, while they are harder with respect to polymers, they are softer with respect to hard plastics. So, that is one case where you can actually mold some softer material into a plastic to reduce its rigidity or Hamaker constant. Also, you know, the combinations are interesting. When you have a, for example, a silicon oxide particle approaching let us say a silicon surface, the Hamaker constant for silicon is greater than the Hamaker constant for silicon oxide. So, what does that imply? The affinity of silicon for the silicon oxide that is approaching is greater than the affinity for the silicon oxide to the silicon. Now, again, that is mostly positive, because that means that if you are trying to make silicon, silicon oxide is not going to act as a contaminant. However, if you are taking a silicon surface and you want to polish it using silicon oxide abrasive, that is not so good, because there is going to be a repulsion. So, the silicon oxide particles may find it difficult to make contact and provide good polishing for the silicon surface. So, you may need to use again additives to improve the contact between the polishing abrasive and the surface that you are trying to polish. So, there are a lot of interesting implications of this type of behavior that we need to be aware of. And again, remember that we are only talking about one type of adhesion force. The net adhesion force is a combination of all the ones that we talked about. So, you may choose a material which minimizes one type of adhesion force, but at the same time it might actually increase another type of adhesion force. For example, if you are trying to reduce Hamaker constants, you might want to use plastics instead of metals, right? That makes sense, but the problem is, from an electrical conductivity viewpoint, plastics are much worse. They are more likely to build up a static charge. So, electrostatic attraction forces will be much greater when you use plastics compared to when you use metals. So, the net adhesion force may actually be increased by using plastics instead of metals. So, you have to think about it in a systems way. You have to think about all the implications of the material pair that you are using on the associated adhesion forces and make the right choice for your application, whether you are trying to maximize the adhesion or minimize the adhesion. Now, the other thing we need to think about is, what role does the hardness of the material and the surface play? If you have the simple theory that we have talked about here is really only applicable when you think about it for the case where, as the particle approaches the surface, there is no deformation of the surface, that the surface remains as a planar surface. Supposing the surface itself is relatively soft compared to the approaching particle, and it actually deforms when the particle approaches, then what happens? So, imagine a situation where initially you have a surface and you have a particle on top of it. Now, when the particle approaches the surface, the next instant you may actually start to see a slight deformation of the surface as it tries to accommodate the approaching particle, and over time you may actually form like a dimple on the surface in which the particle starts to nestle, and eventually this may lead to a situation where you have physical encapsulation of the particle. Now, in such a situation, how do you characterize the Hamaker constant? At t equal to 0, when the particle first approaches the surface, the Hamaker constant will be what we have calculated earlier. But then over time, the Hamaker constant itself remains the same. However, what is changing? Why would the force of adhesion increase with time? If the Hamaker constant is remaining the same, why would the force increase? What is in the equation that will allow that to happen? Well, one is this Z0 in the denominator, right. As the material deforms, the particle can essentially make much more intimate contact with the surface. So remember we talked about the equilibrium distance of separation, that can drop to virtually 0 when you have a deformable material surface or even a deformable plastic, I mean deformable particle. In both cases the intimacy of contact between the two approaching surfaces will be much more, which means that the values of Z0 will be much smaller. And the other reason is dP. Now what do we mean by particle diameter? It is the surface, in reality it is the effective dP that makes contact with the surface, right. In the case of a hard particle approaching a hard surface, the contact area is going to be limited to a very small sector of the particle, whereas as we showed in this illustration, as the particle and or the surface becomes more and more deformable, the effective area of contact increases with time, and force is obviously pressure times area, and therefore as area increases the adhesion force increases as well. So basically when you have two rigid particles in contact with each other and you calculate the adhesion force or you estimate the adhesion force associated with that and compare it to a case where the two bodies are now considered to be deformable, the adhesion forces that develop in the latter case can be orders of magnitude higher compared to the adhesion forces that develop in the first case. Here again this is something that you can use to your advantage or it may work to your disadvantage depending on your process. If you are concerned about adhesion and you want to minimize it, then this would say that basically make sure that you use surfaces that are not deformable, which are hard. And in fact some of these same arguments apply for roughness also. When you have two smooth surfaces contacting each other versus two rough surfaces, again the adhesion forces are different, and the reason for that again is the differences in the area of contact more than anything else. So when you have two smooth surfaces that come in contact or a highly polished particle in that is approaching a surface, the van der Waals force is very high. In fact I'm sure you have heard of the experiment where you bring two highly polished surfaces together, you can almost never take them apart. The force of adhesion are virtually infinite. But supposing now you roughen the bottom surface so that you introduce some asperity and now the top surface comes down, the forces are going to be reduced, right, because the effective area of contact is now only the peaks of the asperities, and so it virtually halves the area that is available for contact. Now if the top surface is also rough, then what happens? Well, that depends. Sometimes it leads to reduced forces, but sometimes it can lead to this interlocking mechanism that we talked about, and it can actually result in an increase in the adhesion force. But clearly the point is properties of the physical properties of the particles and the surfaces, including their hardness, deformability as well as roughness, also play influential roles in determining the forces of adhesion between these particles. Okay. Alright, so in this lecture we have just covered van der Waals force of adhesion. In the next lecture we will start discussing the electrostatic forces. Any questions on what we have talked about today? See you at the next lecture then.